Jnanam paramam dhyayam. Knowledge is supreme.
So in tutorial 3 we have seen 2 problems, and now we are going to continue with the remaining problems of this tutorial. So we will start with the third problem now. So third problem is an exercise wherein you have to express the operator which is given in terms of the exponential e raised to I function of an operator A in Bra-and-Ket notation form using the eigenstate of the operator A on the basis. So this problem is very simple. I can give you a hint of this problem and you can do it. So first of all, we assume problem 3. In this problem what we do is we assume that this operator is normal, that is A dagger A is equal to A dagger. Operator A dagger A is equal to A dagger, and when you operate this operator on a wave function, it will give you some eigenvalue lambda on psi. So if this operator is operated n number of times, what one obtain is psi of n, lambda n, psi of n. Okay. So now this operator can be written in terms of a series, power series. So f of A can be written as Cn A cap. So n times we have operated. So we can write this operator in terms of power series, and this will give you the corresponding terms of the function of f of A. So now if this operator is operated on the wave function, f of A is operated on the wave function, one would obtain the eigen values. So we will write C lambda in terms of Cn. So this is what we obtain. Okay. So this function in terms of the eigenvalues, so these would correspond to the eigenvalues. So now this operator, if I want to write in terms of some operator in terms of the eigenstate as the basis, so we can write this operator as some A prime, let me call A prime as the eigen in terms of the projection operator. So let me call A prime or A1 as some state. So A1 would, when you project out, when you do apply the projection operator, we obtain the eigenvalue of operator A. And similarly for An we can write in terms of A. So the same thing which I just now demonstrated here, and then this can be easily expressed in terms of, so f of A, you can see now directly that f of A can be expressed in terms of the function of the eigenvalue, function of the operator is expressed in terms of the function of the eigenvalue and the projection operator of this basis. Okay. Similarly, one can go and write it in terms of the power series solution. This can be written as power series solution. Okay. That is, you take this and as an exponent of, that is e raised to I f of a prime can be expressed in terms of these bases. So, simply you can rewrite in terms of the eigen vectors in terms of these bases. So, the operator on this basis, and now we go to the next problem. So, in this problem a Hamiltonian operator is given to you for two systems, okay, and you already have an exposure to what does this mean. If the Hamiltonian is written in terms of these eigenvectors, I think you all know by now that this would mean that you can write this operator, Hamiltonian operator, as 1 1 means this when I am writing in terms of matrix. This is a Bra-Henket notation. So, here I am writing in terms of the matrix. So, this would give me 2 2 is minus 1, this is plus 1 plus 1. So, simply I can write it like this. Okay. Now, this if I rewrite as 1 by root 2 1 1 1 minus 1. Okay, so, this is nothing but this is nothing but, I think you have already come across this Hadamard matrix. Okay. So, now we know that what are the properties of this matrix. First, it is Hermitian, then unitary, it is a unitary matrix, it is Hermitian, and you can see from here it has a 0 trace. So, trace is 0. Okay. So, these are the 3 properties of Hadamard matrix, and now you can simply since you know the eigen values of this matrix, which is 1 minus 1, you can obtain easily the eigen values of operator H would simply be what it will be. For 1 minus 1 is for the Hadamard matrix. So, it will be A root 2 and minus A root 2. Okay. So, these are the 2 eigen values. So, using these eigen values you can easily calculate the eigenvector. One of the common way, trivial way to calculate it is by substituting H psi 1 is equal to lambda 1 psi 1, where lambda 1 is the eigenvalue of this operator. So, we have 2 eigenvalues, lambda 1 is A root 2, suppose I take lambda 1 as A root 2 and lambda 2 is minus A root 2. Okay. So, just one example I will just demonstrate. So, H is nothing but 1 1 1 minus 1, and let me call this column vector as some x1 x2, okay, which I need to calculate. This is A root 2 x1 x2, okay, and now it is very simple, you just have to evaluate this. So, x1 plus x2 will be root 2 x1, x1 plus x2 will be root 2 x1, x1 minus x2 will be root 2 x2. Eigen vectors are, so the first one which I just now demonstrated will give you the result okay. This is very simple to check. So, this is the first eigenvector, and the second one you obtain, it is just a few steps you have to calculate, and then you obtain this 2 root 2 minus 1 get 1 minus root 2, sorry, minus get 2, not root 2. So, the first one is this normalization get 1 plus root 2 minus 1 get 2, and the second vector eigenvector will be square root of 2 minus 1 on ket 1 minus ket 2. So, this is the eigenvectors corresponding to the eigenvalue. So, the eigenvalue for this was a root 2, and for this it was minus a root 2. This you can easily check. So, once you obtain the result from the previous this part, when you simplify this, you will obtain an eigenvector. You rewrite it in terms of ket 1 and ket 2. Okay. Go through this problem 5. Consider the state psi as 3i phi 1 minus 7i phi 2, and chi is given by this expression, that is minus phi 1 plus 2i phi 2, where phi 1 and phi 2, these kets phi 1 and ket phi 2 are orthonormal. They are orthonormal, and you have to calculate now 3 things. One is you have to calculate ket psi plus chi and bra chi plus psi plus chi. Then in the B part you have to calculate the scalar product of psi and chi and psi, and check whether they are equal or not. So, from B part we will discuss, B and C part we will discuss later. So, C part says that you have to show that the state psi and chi satisfy Schwarz inequality and triangle inequality. So, you have already seen these inequalities in your regular lecture. This triangle inequality last time we discussed. So, just recollect and just check. This is a numerical check. So, you can just try out this. So, let me start with the first part. Psi is given to you as 3i phi 1 minus 7i phi 2, correct, and chi is given to you as minus phi 1 plus 2i phi 2. Okay. It is very simple, it is just a simple addition, simple exercise. So, this will give me, this is very simple, it will give me 1 plus 3i phi 1. Okay. I am adding the kets, and this is 7i minus 7i, and this is plus 2i. So, simply minus 5i phi 2. Okay. So, this is very simple. When you are adding the two kets, you can add them. Okay. You are using the property of, you can add this linearly and you obtain this result. Now, you have to find out the bra of psi plus chi. So, simply what would you do is just take the complex conjugate of this. Okay. You just take the complex conjugate. So, you will have, what you get is minus 1 minus 3i phi 1, correct, plus 5i get phi 2. Okay. It is very simple to check this. Okay. This was the A part, right. In the B part, you can attempt this problem. You can simply attack it by just putting the bra of psi and ket of chi, and simply by and you know that phi 1 and phi 2 are orthonormal. That means phi 1 on phi 1 will give me 1 and phi 1 on phi 2 will give me 0, simply that. That is a hint. So, you have to check whether this and this are equal. So, what is the guess? The guess would be that chi psi on chi, that is the product psi and chi, will be nothing but, so check this whether you get. Recall, Schwarz inequality would be, you have to see whether this psi on chi square, okay, is the norm of psi times the norm of chi. This is very simple to check. You have to calculate the norm of psi. Okay. So, the norm of psi will be, rather you calculate the the psi square. Okay. Norm of psi will be square root of this. So, basically we are not calculating the square root of this. So, or you can just make it. Okay. So, you have to check whether the psi square chi square is equal to or less than or equal to this. This can be solved by just calculating the psi on psi, that is psi star and chi star, okay, which is few steps, and then chi on psi, which you have already calculated in the previous example. So, whether they are equal. So, this is one part, and in the second part what we do is we have to check the triangle inequality. So, triangle inequality would be, we have seen it last time that you had checked that norm of psi plus chi should be less than or equal to norm of psi plus norm of chi. This is the triangle inequality we have seen last time. In the last tutorial we have proved this. So, which is nothing but here it would be psi plus chi, psi plus chi is less than or equal to square root of psi plus square root of chi. It's again you have already calculated in the previous problem psi square and chi. So, chi square you have calculated, psi square you have calculated. This part you have calculated in the first part of the problem. You have to just take the bra and ket and do the bra and ket multiplication and take the square root. So, it will involve few computation. I am deliberately skipping this so that you do it yourself, try and calculate it yourself as an exercise. So, such problems would be very useful, and in further tutorials we will see more problems, more physics based problems. These were few math based problem except third and the fourth problem. So, this was just to give you an exposure to the bra and ket notation. So, you have to get used to with this bra and ket notation. It is very useful, and you will see it has a it is very useful for doing the calculation. So, you must see to it that these notations, when you do these calculations, these notations are very useful, and you need to have your hands on these expressions, I mean these calculations. So, try these problems yourself with the hint that I have given you in this tutorial. We will continue next time.